Welcome to week one of cryptography and data security. Welcome. Great to have everybody here. Looking forward to a great 7 weeks. Hopefully everyone has looked at the intro video. And today we're going to kind of jump into the introduction of cryptography. We're going to talk about basically on a high level, what is it all about? And then probably more in class and with the homework, we'll get into specific ciphers that were used, but probably are not used anymore, only because things have shifted more from a manual type verification to one that is numerically based on numbers, random numbers, hashing, those sort of things. But I want to get your introduction so you can get a foundation as to where things started and what the ultimate goal is of cryptography and data security. So we're going to start out with a definition. Okay, the definition of cryptography, the practice and the study of techniques for securing communication and data. It is if you looked at things that you probably could go in as far as getting a career in, this is one of them. Cybersecurity, a big portion of that is cryptography and protecting data. Historical motivation, protecting messages from unauthorized sources, digital security, online transactions, securing communications. The four legs of the table, so to speak, of cryptography, the goals are confidentiality, integrity, authentication, and non-repudiation. And we're just going to briefly go over each one of those. Confidentiality, the definition. Confidentiality means that only the intended or authorized people are allowed to read the information. If I send a message to you, I don't want Harry to get that message also. My message is to you. It is a private message that I only want to go to certain individuals. The goal is to prevent unauthorized access. That is one of the things we'll be delving in this course is how do we do that? How do we prevent someone who shouldn't be looking at the data, making sure that they don't see it? Key idea, keep information secret from anyone who should not see it. Examples, encrypting a message so only the recipient can read it, locking files behind a password, restricting access to private data. Integrity. Integrity means that the information has not been altered, changed, or tampered with. When I get a message or when you receive a message, you can be assured that no one has messed with that information or changed it or, even accessed and read it, okay, before you did, okay. So this is basically like getting the integrity part to make sure that what we're sending and what we're receiving hasn't been tampered with. The information stays accurate and unmodified. Examples, detecting whether a file has been changed, ensuring that no one edited a message in transit, and using numerical things, numerical items such as checksums and digital fingerprint to confirm the authenticity of the data that you're either receiving or that you were sending. Authentication. Authentication is the process of verifying the identity of a person, device, or system. This is basically saying that I need to be able to know who sent me information, and you need to know where and make sure that I am the person that sent information if you're looking for information from me. Who are you, and can you prove it? Those are the things that we're going to be kind of deep diving in all through the course. A key idea, confirming someone or something is who they claim to be. Entering usernames and passwords, using fingerprint, face recognition, logging into secure systems with your unique identifier, verifying the source of the information. Again, all of this is basically boiling around data security and using cryptography to, in essence, to enable these things that we're talking about as far as the four legs. Non-repudiation. Non-repudiation means that someone cannot deny having performed an action. I received some data from you, but you are trying to hide the fact that I, in fact, you in fact did send it. Okay, well, non-repudiation says I have proof that you sent the message, and that if someone did get to the data before they were authorized to do so, I know that that individual has access to that information. So that's non-repudiation. Basically, no denial. Okay, as far as information that's passed back and forth between individuals, companies, or entities. The key idea: preventing a person from saying, I never did that, or I didn't send that. Yeah, that is our purpose, to make sure that we can close that hole as far as information is concerned being transmitted. Examples: digital signatures attached to documents, log transactions that cannot be erased, signed emails that verify who sent. So in summary, we looked at the overall, the key purposes of protecting privacy, maintaining accuracy, confirming who is involved, and establishing accountability for information that's passed back and forth. Okay, so that's basically a very high 10,000 foot level as far as overall what we will be delving into. We'll be getting into specifics on each one of those as each week goes along, including with your project. But again, that's just again an introduction into the major components. Three major branches of cryptography: symmetric encryption, asymmetric encryption, and hash functions. Everything that we're going to talk about is going to fall into one of those three categories as far as the branches of cryptography. Okay, so symmetric encryption. Symmetric encryption is the method of protecting information in which there's one secret key, and it's used by both encryption and decryption. So there's one key that will encrypt, and I'm going to use that same key to decrypt the information. That is a symmetric encryption. Both the sender and the sender must know and protect the same shared password. Okay. Key point of that both the sender and receiver have the same information. One shared secret key locks and unlocks information. Example spelled out, advanced encryption standard, data encryption standard, triple data encryption. So that's AES, DES, and TDES. Okay, are the acronyms that go with those. The strengths: okay, symmetric is very fast, okay, and excellent encryption for large amounts of data. In order to have that information, having that single key cuts down the time that we would need to basically figure out what the key is or what the key should be. Weakness: you must find a secure way to share the secret key. Okay, both of us are using the same key. I have to find a way of moving that key from me to you, or vice versa, from you to me, without somebody in itself trying to find out what the key is, so that they won't be able to steal data and get to data they shouldn't. You must find a secret way. It becomes difficult to manage when many users need secure communication. You can't have a different key for 1,000 different users that you may be sending information to. But again, you must have a situation where the larger the number of individuals that are using that secret key, the more possibility that that information could in fact be accessed by someone who shouldn't have it. Asymmetric encryption. Okay, we talked about asymmetric encryption, public key encryption. There's another name for it. Asymmetric encryption uses two different keys, but mathematically connected keys. Okay, so in this case, we're talking about having two keys. One is a public key, which is used for being able to send data. So somebody might have the public key in order to be able to send data to me. But I have the private key. Okay, and that private key is the only way that that information can get decrypted is by the private key. So here we have a public key which anyone's allowed to see and use to encrypt information. Okay, taking regular data and encrypting it, and then a private key which only the owner keeps secret and uses to decrypt the information. So any number of people can encrypt with it, but only a limited number of people can decrypt the information that was sent. A person can share their public key openly because only private keys can unlock messages protected by the public key. The key idea is the public key locks the information. The private key unlocks the information. Examples, reverse Shamir ideal method, elliptical curve cryptography, and the Diffie-Hellman key. We'll be going through some similar uh, basically encryption methods and decryption methods. But at least one of these we'll be going through. But this is for your reference, if you want to go ahead and do some lookup on these and say what is behind the public key, private key process that is basically embedded in these three particular methods. The strengths, no need to secretly exchange a key ahead of time. Don't need to do that. Enables digital signatures, secure key exchange, and authentication. Weaknesses, much slower than symmetric methods, usually used to secure keys or small pieces of data and not entire large files. Hashing functions. A hashing function takes any amount of input, text files, passwords, texts, and produces a fixed length output called a hash or digest. A cryptographic hash function is designed to be one way, meaning you cannot reverse the hash to reveal the original information. One way is fingerprint data. One way fingerprint data. So basically, and I'm going to leave it open on if you caught what I just said, is that okay, if the hashing function will produce something and you're not able to get to it, okay, because it can't use that hashing function to decrypt, then how do we do that? That's some of the things we're going to cover in class. Something to look forward to. Remember it. Okay, we're going to come back to it. Essential properties, deterministic. The same input always produces the same output. One way, the original message cannot be reconstructed from the hash. Collision resistance, extreme difficulty to find two different messages that produce the same hash. Avalanche effect, even a tiny change in the input results in a completely different output. By changing one byte, okay, in a message could change the whole, presentation of the hash that is basically going to be produced from it. Examples, secure hash algorithm 256, secure hash algorithm 3, message digest 5, no longer secure. We will be talking about these in detail as far as how they work and how we can basically transform data to protect its contents better. Common uses, storing passwords, safety, checking whether files have changed, digital signatures, blockchain systems. Classical versus modern cryptography. We're going to be jumping more in this in week 2, next week. Basically, how we handle classical cryptography before, without having basically a numerical basis, is probably you can think of it as doing things manually, doing things on a slide rule, okay, versus doing things on a computer. Okay, you get the same results, but that's the comparison of a classical and modern cryptography. And you'll see there's a vast difference between what we're going to start out with and what we're going to talk about this week and concentrating this week, and then eventually an introduction into numerical modern day cryptography next week. Okay, again, real world applications that all of this applies to, on the internet as far as URLs, HTTPS, banking, messaging apps, digital signatures, blockchain. We will be touching mostly all of that. Okay. Okay, one thing I did want to introduce you to first, and before we jump into next week, is frequency analysis. You'll see this term probably several times, and I wanted to make sure that we just jump off the start and make sure that we have an understanding of frequency analysis. Definition is the study of letter patterns, frequencies in ciphertext to break substitution ciphers. Okay. Why does it work? Languages have an uneven character distribution. Okay, for example, E is common in the English language. A is common in English language. IOU is common in English language. Okay, the classical vulnerability monoalphabetic substitution ciphers map each letter the same way every time. And that's basically say if I had Mac, M-A-C-K, and whenever I have an M, I'm going to replace it with a Z. Whenever I have an A, I'm going to replace it with a T. Whenever I have a C, I'm going to replace it with another letter. So it's basically a one for one, taking your particular message and transforming or encrypting that such that each one of the letters in the message basically becomes with some other letter in the language. That's basically what we have here when we talk about substitution vipers. Excuse me, substitution vipers. We're talking about substituting data, substituting letters, one letter for another. That's the substitution. We're going to talk about transportation ciphers later, and other types of ciphers. Why it works, languages have an uneven letter distribution, okay, classical vulnerability, monoalphabetic substitution ciphers map each letter the same way. We're basically going to be fixing this with a polyalphabetic substitution. We're going to be talking about that and talking about the Vigenère method. Basic techniques, count letter frequencies. I have a letter that has A in it, and I've always substituted a T for. And I look at my message, and I got a bunch of T's. Okay, then I'm probably going to I have the possibility of looking at anywhere I have a T and see what happens if I replace an A with it. Okay, what happens if I replace an I and O or U? At some point, I might be able to get to enough of the message to be able to figure out what it is without having to know the entire message. Okay, so basic techniques, count letter frequencies, compare to known English frequencies, infer, okay, mappings, infer that based on what I see, what I can deduce. Again, example, A, T, A, O, I, N are common letters that for basic mono substitution, the more times these appear within a encryption, the more times it is probably going to be one of these letters, okay. Rare letters Q, X, J, Z aren't used that often in messages, so we don't have that luxury of being to maybe deduce what these particular ones are. Countermeasure, I just mentioned the polyalphabetic ciphers, the Vigenère, and how that will change the whole process dramatically to where substitution ciphers do have a very good place in cryptography. Okay, frequency of analysis is less effective on strong ciphers, but it is the foundation for cryptanalysis and in cryptography. We're going to be taking this, using your homework assignments and our discussions in class. We're basically going to be going through three types of ciphers and how they work. We also be talking about your project. I'll go ahead and introduce that to you now. Depending on when you see this, it might be before or after we've talked about it in class. But your particular projects that you're going to be having, and I'll have your projects assigned by the time we meet in class for those who are face-to-face. I will be communicating with our online folks here in a little different way, but I will have your particular project that you will work on. And each week of the project, Okay. You will basically be doing something on the project that aligns with what's being discussed in this given week. So today we're talking about ciphers and introduction. Your first entry in your project will be putting a cipher in place, some cipher in place that will basically build on the information we just talked about today, as far as the types of ciphers, asymmetric, symmetric, and how we can use that in the particular project that you're going to be doing and basically be building by the end of the semester. So that's the introduction. Look out in your resources. You'll see your resources of the three ciphers we're going to be talking about as an introduction. And then also the information as far as what the requirements are going to be for the project, both for this week and for the following 7 weeks, what the expectation is. The assumption here is that you do know a programming language. These specs are basically written for VS Code. Okay, and that is the language that basically primary. Doesn't say you have to use VS Code. Okay, you'll see the specifications on what's being done. If you like Python, okay, you say, well, I could do that in Python. Fine, no problem. So as this is really not a programming language, and in fact, I want to make sure that you know that what we're doing is we're going to be using a lot of reuse. And reuse means that we're going to be taking code that may have already been written in order to build and illustrate the different concepts that we want to talk about. So if I'm going to be doing a Caesar cipher, okay, I'm not expecting you to write the code for the Caesar cipher. I'm expecting you to find that code somewhere and implement that code. Excuse me, and implement that code in your particular project. So it's not to write it, but you have to know basically what the particular program or the snippet is doing and how you're going to implement that into your project. So not really a lot of coding other than you know the language. Assumption is you know the language, but more of I'm going to be using code that does this, I'm going to be using code that does that, and I'm going to take that, put it together, and kind of build on my project from week to week. Okay, well, that's going to be it for week one. If any questions, we'll be talking about, uh, yeah, one of these things I'll be requesting your passwords, but I'm not going to discuss that here. We'll do that in class or directly email us through the online group. Okay, so we'll be talking about that on when we get together. Hope to see you soon. Hopefully, we will have a fantastic 7 weeks in talking about cryptology and data security. Everybody have a good one. See you soon.